With these bell-shaped curves, there's going to be all sorts of different number lines and scales that we can use because it's all based on the mean and standard deviation. So again, like this rainfall example, while the shape of the bell-shaped curve will stay the same for any distribution of numbers, what'll change is the number line. So in this case, we have our specific number line that we get based on our mean and standard deviation. But as we can imagine, as soon as we look at something different, we'll get a different number line out based on that scenario. So what we want to be able to do is, sorry, I was speaking and writing. Hold on, there we go. And then we have 24 and then a 16. What we want to do is standardize this number line so that we can compare things that have different means and standard deviations to each other. And the standardized model is going to think about, instead of writing a number line specifically to mean and standard deviation, let's start thinking about distance away from the mean. And this distance that we want to use is going to be based on standard deviations. So we want to do distance away from the mean based on number of standard deviations. So what this is going to look like is, if we have our number line here, if we start with the mean, so we just start in the middle of our graph here. If I want this idea of, well, how far away is 40 from the mean? Well, it is exactly the mean. So what we're going to start seeing with these curves is we'll have 0 right in the middle. That's our expected value. Then say we go to the right. So if we go to 48, that distance there, so in terms of rainfall, it's 8 inches of rainfall away, but based on number of standard deviations, it's 1 standard deviation away from the mean. So in this example here, we're kind of using 8 as our ruler based on this scenario. If we had a case with different standard deviations, then that new standard deviation would become our ruler. But now we're saying if it's 8 inches away from the mean, then it's 1 standard deviation away. So what we would do is translate that 48 into this positive 1. And then 56 is 2 standard deviations above the mean. So we just translate that to a 2, and 64 is 3 standard deviations away from the mean. So we get this scale based on standard deviations away from the mean. Now, when we go below, we don't want to see the same 1, 2, and 3, because if we just say 2 standard deviations away from the mean, we would want that to translate to just 56, just a single number. So when we go below the mean, they're negative values. So 32 would be 1 standard deviation below the mean, which would be a -1, and 24 would be a -2, and then 16 would be a -3. So we get a scale based on standard deviations away from the mean, and these values that we're listing here, these 0s, 1s, 2s, and 3s, those are z-scores. So a z-score is a specific distance based on number of standard deviations away from the mean. So our calculation for z-scores actually uses this formula right here. In the numerator, you take your data value minus the mean. So let's say we did that with 48. If we actually wanted to find the z-score for 48, well, we would be using x is our value of 48. We have a mean of 40 and a standard deviation of 8. So in the numerator, what we want to do is take our data value minus the mean to figure out the distance away. And then we want to divide that distance up by standard deviations, which in this case is an 8. So that would simplify to 8 over 8, which is a +1. Say we did that for 32. So 32 would be our data value that we want to compare to the mean and standard deviation. So subtract the mean to get the distance away, divide that up by 8, and that would be a -8 over 8, which is a -1. So we could have found those z-scores using the formula, and when we get z-scores when we use data values that aren't exactly a certain number of standard deviations away, we may be getting decimals out. So I'll need to use this calculation. So this number line for our bell-shaped curve is called the standard normal model. It's a distribution specific to z-scores. So here we can see some things changed in our notation. When it's just a normal distribution, remember we use that capital N with some mean and some standard deviation. In fact, we just said X was defined by its normal with some mean and some standard deviation. What we do here is we change to Z as our variable, because now we're looking at z-scores specifically. And then it'll be normal, which just tells us that we have a bell-shaped curve. And then with these z-scores, as you can imagine, with our rainfall question up here, we had this number line based on means and standard deviations. If I did this for a different data set, the same thing would have come out in terms of our z-scores. The scale of 0, 1s, 2s, and 3s would line up every single time. So with our standard normal curve, the mean is always 0, because that'll always be stuck in the middle, and then our scale for standard deviations will always be 1. So just be careful in terms of wording of problems. If they say we have a normal model with some mean and some standard deviation, you'd be using X in your normal curve. If they use the word standard normal always uses mean of 0, standard deviation of 1. So just be careful of that word standard popping up. But if we have our standard normal distribution, it's always going to go 0, 1, 2, 3, -1, -2, -3. So it's standard normal because it standardizes the values so we can use it for any scenario. Given any distribution of X values with some mean and some standard deviation, we can switch it to z-scores. And we want to do that to eventually use these things called a z-score table to find areas under the curve. It also lets us compare to unlike events. So with this number line, what we can see in terms of what's expected and unexpected for our z-scores, which is what all these values are along the number line, if you're close to 0, that's really what we expect for our data. And that's our expected value. I mean, if you get a z-score of exactly 0, that means you're exactly at the mean. Then, as you move above, if you're in this positive region, that means your value landed above average. And then if you're in the negative region, it means you're landing below average. What we also have is that rule that we talked about with the empirical rule, which is that if you get to 2 standard deviations or above, or 2 standard deviations and below, those results are considered unusual. So if you get z-scores out in those regions, those would be considered unusual data values. So say we did a calculation and the z-score came out to 2.85. What we can see is it landed above average because it's positive, and it's unusually above average because it's so far out there in terms of what's expected. So now what we'll do is we'll compare 2 unlike events by using these z-scores. So this can be nice when you have 2 things that operate on a completely different scale and see which was more extreme or what was closer to expected. But what's going to be key is thinking about the scale in terms of z-scores and seeing where we're landing on this number line of using a middle of 0 and then having our whole numbers above and below, and seeing that typically if we land then 0 to 2, that's pretty expected. If we land outside of that range, it's unusual. And then as far as comparing 2 values, the key is keeping in mind that landing at exactly 0 is the most expected thing for our data, because that's the idea of being average. But then the further we get away from that, the more unexpected it gets. So what we're going to do is compare rainfall in Portland to wind speed in Chicago. So we're going to have these 2 different distributions where Portland is operating with a mean of 40 and a standard deviation of 8. And then for Chicago wind speed, they say there's a mean of 10 and a standard deviation of 2. So what this tells us, just from general knowledge, we know that rain operates differently than wind speed. Different measurements, rainfalls in inches per year and wind speeds in miles per hour. We can't compare them directly, meaning that when they tell us that Portland had rainfall of 24 inches and Chicago had a wind speed of 13 miles per hour, and we want to see which is more extraordinary, we can't just compare the 24 to the 13 because they're on a different scale and they operate with different expected values and how they spread out. And that's where we need z-scores. We need to figure out how does that one data value compare to the center and spread that we expect. So for Portland, what we can do is find that z-score by taking that data value of 24 and compare it to the mean, and then divide by how many standard deviations away it is. So that if we just standardize it to this distance away from the mean in standard deviations, mean in standard deviations, we can compare the two values to each other instead of when we're stuck with comparing 24 to 13 and we can't do that. So our z-score here, when we simplify 24 minus 40 and then divide it by 8, should give us a -2. So what this would tell me is that 24 inches of rainfall in Portland is 2 standard deviations below average. So again, positive versus negative. If it's negative, it's below average. Positive is above average. And then the 2 is just giving us a distance away from the mean in those standard deviations. So if we did the same thing for Chicago wind speed, take our data value of 13 minus the expected value of 10 and divide by 2, and that's going to be a positive 1.5. So 13 miles per hour wind speed in Chicago is 1.5 standard deviations, in this case above average, since it's positive. So now trying to figure out which is more extraordinary, which is really just looking for which was furthest from what was expected. If we go back to that number line we were making, we can see where our results are landing. So Portland landed at -2. So that was Portland rainfall. And then Chicago wind speed landed at positive 1.5 there. So if we think about which was further from expected, well, Portland rainfall had this distance of 2 away, while Chicago only had a distance of 1.5. So Portland had the more extraordinary results because it was further from expected. So write that here. Portland had the more extraordinary results. And it was because it was basically further from 0. So you could think about comparing the absolute value of the two numbers here. Sometimes it matters if it's above average versus below average, like exam scores. If you want to see who did better on a test, you would want the values to be positive. So in terms of standardizing z-scores, it doesn't change the shape. So while all of our initial distributions were bell-shaped, if you change to z-scores, it stays bell-shaped, and it makes the center a 0, and then we get that standard deviation of 1 out to get basically a comparable scale. And then we can look at Chicago wind speed and Portland rainfall at the same time on the same number line. Now, let's look at one more example of comparing two values with different scales. We have students taking a French and mathematics test. In French, this one student got a score of 82. In math, she got an 86. And then what they give is a distribution for the scores for each test. So the idea being that different tests just operate differently. So with the French test, they say they have an expected score, so a mean of 72 and a standard deviation of 8. And then with the math test, they expect a score of 68 with a standard deviation of 12. So in terms of comparing these two tests, we could see we expect lower scores for math, but there's also more variability to the scores for math. So that's something we need to take into consideration, is also how did the score spread out? Because if there's a lot of variability, then we could expect to be kind of far from the mean and it wouldn't be that unusual. Whereas like with the French test where there's a smaller variability, the idea would be that we really expect that 72 and we wouldn't expect to be that far away from it. So what we need to do is find the z-scores for each of these scenarios. So for French, we would take her score of 82 and take out the mean and then divide by our standard deviation of 8. And that should give us a z-score of 1.25. Then for the math test, she had a score of 86 and we want to compare that to the mean and divide that up by our standard deviations, and that was a 1.5. So in terms of which score she did better on, we could compare them on that number line. 0, 1, 2, and looking at how far away from the mean was she. So for the French test, she was at 1.25, and then for math, she was at 1.5. So that math score is further above average. So what that would mean is she did better on the math test. The math score was better. So z-scores let us compare values that have different scales to them and see kind of where they land in terms of what's expected and the spread of the data. What's going to end up happening is we want to use this bell-shaped curve to end up finding the areas that we talked about in the first video. We want to change any distribution that we're given into the standard normal, which is going to mean calculating z-scores first. So any cutoff values that we use for finding area are going to be z-scores, and then we can look at like finding area above or below or between two values, and that's where we're going to need to look at z-tables.